We will start at 6. We'll wait for anyone to join. This is week 6 of the upper thermodynamics course. So we are looking at internal combustion engines. So previous week we saw how an internal combustion engine works, what are the parts of an internal combustion engine, and how the process occurs over in an internal combustion engine. And we also saw two types of the internal combustion engines which you can have. One was a 4-stroke engine and other was a 2-stroke engine. So, and also we saw that in 4-stroke engine, a power cycle, a power or working stroke happens every 2 revolution, and in a 2-stroke engine you have working stroke every revolution. So that was the two kinds of engine which you saw. So now we'll see processes which happens in an internal combustion engine. So usually you can have three processes. One is an petrol engine or spark ignition type process which happens in an Otto cycle, and then you have a diesel cycle. So in a compression ignition engine you have a diesel cycle, and the third is you have a dual cycle. So dual cycle is a mix of both Otto cycle and diesel cycle. So Otto cycle, it was owned by Otto, so it was named after him, and same with diesel. So we look at these cycles, these three cycles. We'll see numericals on this, and also we'll look at some of combustion related problem in this engines. So first is an air standard Otto cycle. So before going this, I'll just give you a recap on the internal combustion engine, how the process occurs in internal combustion engine. So to start with, you have first an air mix and fuel mixture intake which is happening, and that happens in a suction stroke. So your piston, assuming it's in a top position, top dead center, it traverses to the bottom dead center, during which there is a vacuum created and valve opens, and the air and fuel mixture is let in. And after coming in, you are compressing it. So again the piston will move from bottom dead center to top dead center. So, and you always have a clearance volume. So the fluid and air, fuel and air is getting compressed. So this will cause an increase in temperature and pressure. So in a compression ignition engine, what will happen is this will fuel be injected, or the fuel which is there will start combusting because of this rise in pressure and temperature. In an spark ignition engine, you initiate the combustion process with a spark. You send an electrical energy in the spark, and that creates an electrical energy. It starts the combustion process in a spark ignition engine, and then because of the combustion, there is an increase in pressure, and it will start pushing the piston, and it will start doing work. So the piston will be moving down, and then it will again come back, and during that process it will start pushing the exhaust gases out. So this was the four different stages in a internal combustion engine. So that we'll see in an Otto cycle. So if you see, it is starting with the top dead center, so at stage 6. So from there you are moving to the bottom dead center. So this is the suction stroke. So in this case, what will happen is your fuel and air which are coming in, and then you are compressing it. So that happens at process 1 to 2. So you are compressing from bottom dead center to top dead center. You are compressing it, and then in the spark ignition engine, initiating the spark, there is a combustion process. So that's like an heat addition process. It happens at a constant volume. So it has moved to the top dead center. So you are assuming that stays in the place, and your energy which is provided, it is happening at a constant pressure. So constant volume. So it happens at 2 to 3. So constant volume heat addition, and then 3 to 4 is the working stroke. So because of the combustion and heat energy which you are coming in, the piston will start doing work. So that is the working stroke. So 3 to 4, and then again 4 to 1, it and 5 to 6 it will be exhaust process. It's in actual cycle. So in this case we are depicting that as an ideal cycle. So you have first compression stroke, so and then so you can neglect whatever inlet and air is coming in and exhaust is going out. So you can assume there is some fluid in the engine and it's going through this 4 processes. So 1 to 2 is an reversible adiabatic compression, and then you are supplying some energy, heat, which is happening at constant volume, 2 to 3, and then 3 to 4 is your adiabatic expansion, and then 4 to 1 again it completes the cycle. So this again happens at constant volume. So this is the ideal depiction of your internal combustion engine. So this is called an Otto cycle. So same thing I have shown in a temperature entropy diagram. So 1 to 2 is a reversible adiabatic process. So as an isentropic process, entropy is constant, and then 2 to 3 is a isobar, and similarly 3 to 4 adiabatic, and 4 to 1 it's an isobar. So in this Otto cycle you have 2 isobars and 2 reversible adiabatic process. So if you find out efficiency, so efficiency will come out to be 1 minus 1 by RC. So RC is the compression ratio raised to power gamma minus 1, or here I depicted as K. So this will give you the efficiency formula for an Otto cycle. So other way is you can estimate the work done. So work done will be the area under this PV diagram cycle. So that is the net work which is generated divided by the heat added in the process 2 to 3. So substituting that and simplifying it will give me this expression 1 minus 1 by R raised to power gamma minus 1. So this is an Otto cycle. A slight variation to this is a diesel cycle. So in this case what happens is your heat addition is not happening at constant volume, but it is happening at constant pressure. So this is similar to an diesel engine. So in this case you are that's the variation. So there, instead of constant pressure, the rest of the process will remain same. So in this case, your previous case Otto cycle, the heat addition was at constant volume, so at top dead center, when the piston is at top dead center. So in this case we are assuming that instead of its constant volume, it is at constant pressure. I here this 2 to 3 and 4 to 1 is not isobar, it's isochoric process. Sorry, while explaining this diagram, I told it as isobaric, it's isochoric. 2 to 3 and 4 to 1 is isochoric. So here again, so in the TS diagram, this is how the process will look. So again there are 4 processes. So here two adiabatic, one is adiabatic expansion and one is adiabatic compression, and the other is you have constant pressure heat addition and constant volume heat rejection. So here 1 to 2 you are compressing it at adiabatically, then 2 to 3 is isobar, so constant pressure heat addition. 3 to 4 is an expansion, adiabatic expansion, isentropic expansion. So 4 to 1 is again a constant volume, so isochoric heat rejection. So in this case this is how the expression will be. So 1 minus 1 by RC raised to power K minus 1 into beta raised to gamma minus 1 by gamma into beta minus 1. So beta is the volume ratio between the constant pressure process, so V3 by V2. So and compression will be your bottom dead center by top dead center. So that is the compressor volume ratio. So this is how the expression will look for a diesel cycle. So the dual cycle, as I told, is a combination of these two. So instead of assuming that your heat addition is happening at constant pressure or a constant volume. In this case it's happening in between, so you have both constant pressure and constant volume. So this is how the cycle will look. So again the rest of the process will be same. So you have adiabatic compression, and then some amount of heat addition is happening at constant pressure, and some amount is happening at constant volume, and some amount is happening at constant pressure. And then 3 to 4 is again adiabatic expansion, and 4 to 1 is an isochoric heat rejection. So similarly you can see in the TS diagram, so 1 to 2 is a isentropic process, and 2 to x is an isochoric, and x to 3 is isobaric. So you can see the difference in slope. And 3 to 4 is a reversible adiabatic expansion, and 4 to 1 is again isochoric heat rejection. So in this case again this is how the efficiency can be written. So this alpha and beta is all with the pressure ratios and volume ratios. We will see in the numericals how to define this and how to solve this. So this is how the expression will look like. So easier way is instead of remembering this, we can estimate the total work done, and we can find out the heat added in the process. So 2 to 3 is the process where heat is being added, so that will give you also the efficiency formula. So this is a simplification of that. So now we have seen this 3 cycles, so Otto, diesel and dual. So how, if we compare, how it will look like. So if we have same compression ratio and heat rejection, so we have superimposed all 3 cycles here. So 1 to 2 is the process remaining same, you have reversible adiabatic compression. Then if you go 2 to 3C, then this becomes a diesel cycle because this is at constant pressure. But and if you go 2 to 3A, that is an Otto cycle. So that's where we are assuming that your compression ratio is same. So 1 to 2 is same, your volume at state 1 and 2 is same, so the ratio will be same for if you are comparing 3 different cycles. And your heat rejection, amount of heat which is getting rejected, is also same. So in this case what happens is the Otto cycle will have a maximum efficiency, and then it comes dual, and then diesel. So that is also evident from the diagram. If you see, your work done is more in the Otto cycle. So even though heat added is also will be slightly larger for Otto, but the net efficiency which you will get is more in an Otto cycle. So efficiency in Otto cycle will be more, then comes dual, and then diesel. So similarly the process is also shown in a TS diagram. So 1, 2, 3A, 4 will be an Otto, and 2x, 3B is a dual, and 2 to 3C is your diesel. So now we saw that as a if you have 3 cycles with same compression ratio, and we are limiting the maximum pressure which you can have, because ideally this thing, practically speaking, you have a limitation on how much pressure you can have in an engine. So if you are going till that pressure, so what will be the case? So in this case you have different compression ratios. So 1, 2A, 3 will be your Otto cycle, because your pressure is increasing at constant volume, so you cannot go anywhere closer. If you so then 2E3 becomes Otto cycle, then 2BX becomes your dual cycle, and 2C is the maximum compression which you can have in a diesel cycle. So in this case, if you see, there is a maximum compression which is happening in the diesel cycle, and also if you see the work done, the area under the curve for diesel cycle is more. So again in this case your efficiency in the diesel cycle will be more then comes dual, and then at last will be auto. So uh, simply speaking, if you have same compression ratio, then auto cycle will have the maximum and diesel will have minimum. But if you have limitation on same maximum pressure and temperature, then diesel will have the maximum efficiency and minimum will be the auto, the other way around. So this gives us the comparison of all three cycles. So with this we'll move on to see some numericals and MCQs. So the first one is, which one of the following process is irreversible in nature? A. Isothermal process, B. Adiabatic process, C. Throttling process, and D. None. So maximum, if you see adiabatic, you are considering is to be an reversible isentropic process. It's all first two can be assumed to be reversible process, but throttling cannot be a reversible process. So in this case, it's just you're wasting your your pressure, whatever is there, you're passing it through an orifice, you have lost that energy, so you cannot bring that back. So other you can assume it to be a reversible process, but throttling cannot be. So this will be a irreversible process out of three. So throttling is the irreversible process in nature. The next question is, an Otto cycle consists of dash A, 2 isothermal and 2 isentropic process, 2 isentropic and 2 isochoric process. See, 2 isentropic, 1 constant pressure and 1 constant volume process, 2 isobaric and 2 isentropic process. So Otto cycle is what we first saw. We have reversible adiabatic compression, so then we have constant volume heat addition, so that is isochoric, then adiabatic expansion, that is isentropic, then constant volume heat rejection. So you have 2 isentropic and 2 isochoric processes. So answer is option B. So next is, for same maximum pressure and temperature, the air standard thermal efficiency for a diesel cycle is higher than Otto cycle. So here this is what we saw now, just the comparison of 3 cycles. So for maximum pressure and temperature, so a limitation on pressure and temperature, so in this case diesel will have the largest efficiency. So they have given the air standard efficiency of diesel is higher than Otto, so it is true. So next question is, the Otto cycle and diesel cycle have the same compression ratio and they undergo same amount of heat rejection. Which of the following statement is correct for air standard efficiency? So this is again the same comparison which we saw. Here they are saying it is at same compression ratio and same amount of heat which is rejected. So in this case we saw that Otto cycle was much more efficient than your diesel cycle. So you have constant compression ratio, then Otto. If you have limitation on maximum pressure, constant maximum pressure, then you have diesel, that is efficient. So in this case it is Otto cycle. So A option, Otto cycle is more efficient than diesel cycle. The next is, in dual cycle heat addition takes place at dash A at constant volume, B first at constant volume then at constant pressure, C constant pressure, and D none of them mentioned. So this is also simpler one. So which you saw, Otto happens at constant volume, diesel happens at constant pressure, and dual happens at both. So you have constant volume, then you have constant pressure. So answer is option B. The next question is, the actual volume of charge admitted in a 4-stroke engine is dash. A equal to the stroke volume, B equal to stroke volume plus clearance volume, C less than stroke volume, D more than the stroke volume. So what do you think will be? What will be the actual volume of charge admitted in a 4-stroke engine? So answer is less than stroke volume. That's why you define a efficiency called volumetric efficiency. So that basically says the volume of your charges, your air plus fuel mixture, which is coming in, divided by the swept volume, or we can write in terms of mass also. So mass which is coming in divided by your density into swept volume. So that gives you a volumetric efficiency. So that basically defines how much amount of actual, even though theoretically you should get the swept volume, but you don't get the swept volume, because during exhaust all the gases will not go out, and there will be some fluid which will charge which will already be present, and because that is also getting compressed, so when you are expanding, it will not let the valve to open in fully, and because all the valve timings and so on, you will not get the actual theoretical swept volume. So you will get less than the stroke volume. So answer is option C. The next is, if the compression ratio of an Otto cycle is increased from 5 to 7, then the percentage increase in air standard efficiency will be dash. So we are saying increasing compression ratio of Otto cycle from 5 to 7. So this is easier. We can find it using the efficiency formula for Otto cycle. So this is how it will be. Your efficiency 2 by efficiency 1 equals your compression ratio 7 by 5 raised to power 0.4, assuming your gamma is 1.4. So this is just going back to the previous formula, Otto cycle formula. So efficiency is 1 minus 1 by compression ratio raised to power gamma minus 1. So this is increased from 5 to 7. So efficiency 1 will be 1 minus 1 by 5 raised to power gamma minus 1, which is 0.4, and efficiency 2 will be 1 minus 1 by 7 raised to power 0.4. So you know two efficiencies. Percentage increase will be the delta efficiency. So this actual top is delta efficiency. So it will come out to be close to 14. So there will be a 14% increase in your efficiency. Next is the self ignition or pre ignition of auto ignition is desirable for SI engine. Answer is false. You don't want self ignition. So self ignition is the fluid combusting itself without you doing any spark energy input. So that is more desirable in case of an compression ignition engine. So because you compress it, because of the raise in temperature and pressure, the fluid will start combusting itself. But in SI engine, you don't want that. So this is false. Next is, the working cycle of an 4-stroke engine is said to be completed at dash number of revolution. So this we have seen 4-stroke engine and 2-stroke engine. So 2-stroke you have working cycle in every one revolution, but in case of 4-stroke engine you have it every 2 revolutions. So you have because you have that 4 processes which is happening at all the half of the revolutions. So it takes a cycle to complete in 2 revolutions, and out of that 4 processes you have one working stroke. So the cycle completes in every 2 revolutions. So answer is option B, 2. Next is, in air standard cycles, it is assumed that the real open cycle is changed to closed cycle by assuming that the combustion products exhausted to atmosphere are fed back with fresh charge in the intake system. So answer is true. So this is what I told you while explaining the Otto cycle. So that actual cycle you are depicting in Otto cycle as a closed system. We are not assuming any intake or exhaust which is going on, but you have some fuel which is already there and it's going through the process. So that's what is being asked here. So answer is option A, 2. So with this we'll move on to see some numericals on Otto cycle and diesel cycle. So the first one is, you have cylinder condition at the start of compression in a SI engine operating on an air standard Otto cycle are 60 degrees Celsius and 98 kilopascal. So this is how SI engine, so can it's already given Otto cycle. So the Otto cycle process is given here. So they are saying that at start of compression, so at intake it will be 1, we have your temperature is 60 degrees Celsius and pressure is 90 kilopascal. The engine has a compression ratio of 9.5:1 and uses gasoline with air fuel ratio as 15.5. So then you have compression ratio just given and also air fuel ratio. Your combustion efficiency is 96% and it can be assumed that there is no exhaust residual. So combustion efficiency is also given. So we need to calculate temperature at all states in the cycle, and B, pressure at all states in the cycle, and C, specific work done during power stroke, then D, heat added during combustion, E, net specific work done, F, indicated thermal efficiency. So we can we'll go one by one. So in this case then to find out temperature we have to solve all of the 4 processes. So in this case we will solve only 1, 2, 3, 4. We will neglect the 5, 6 process, which is intake and exhaust. As I told also in the previous MCQ which we saw, we are assuming this as a closed cycle. So the process will be 1, 2, 3, 4, and 1 to 2 is reversible adiabatic compression, 2 to 3 is constant volume heat addition. So that will give me the option D. How to solve that? So we have to use this 2 to 3. Then 3 to 4 is the work done, specific work done during power stroke, that is the power stroke. Then 4 to 1 is a heat rejection. So we'll see how to solve this. So first one is we know in inlet temperature and pressure. So inlet temperature is 60 degrees Celsius or 333 Kelvin. Your pressure is 98 kilopascal. So now we know the compression ratio. So we know the volume ratio between 1 and 2. So that is the compression ratio. So, and we also know that it is an reversible adiabatic process. So PV raised to power gamma equals constant. So if you substitute the ideal gas equation, you can write it in terms of uh, temperature and volume. So T2 by T1 will become V2 by V1 raised to power gamma minus 1, and V2 by V1 is nothing but the compression ratio. So, and the gamma value is here assuming at gamma is 1.35. So substituting, you have T2 equals T1 into your compression ratio raised to power gamma minus 1. So temperature at state 1 is known, is 333 Kelvin. So 333 into compression ratio is 9.5 raised to power 0.35. So this gives me your temperature at state 2 is 732 Kelvin or 459 degrees Celsius. Here I am converting it to degrees Celsius because the question is asked in degrees Celsius. Then again similarly, just like temperature, I can find pressure. So pressure is P2 by P1 equals gamma V1 by V2 raised to power gamma. So again compression ratio is known and pressure is known at inlet. So 98 into 9.5 raised to power 1.35 gives me 2047 kilopascal. So this because we have to find both temperature and pressure at all states. So I have found out at state 2. Now we are doing an heat addition. So heat addition is happening at constant volume. So whatever heat added is equals to your change in internal energy. So your change in internal energy will be m dot Cv delta T. So m dot here is nothing but your mass of fuel plus mass of air, and air fuel ratio is mass of air divided by mass of fuel. So if you see, it will become mass of fuel plus air into Cv T3 minus T2 divided by mass of F, and that will be equals to your calorific value. Your combustion efficiency is given. Okay, one missing in the question is your calorific value of the fuel, which will be equal to 43000 kilojoule. So that is given. Q is given. Calorific value will be given for the fuel. So Q will be 43,000 kilojoule, and your combustion efficiency is given as 96%. So into 0.96. So if you see, the total heat added will be mass of fuel into calorific value into combustion efficiency. So that mass of fuel which is divided on the right side to make it look like air fuel ratio plus 1 into Cv T3 minus T2. So now the only unknown here is your temperature T3. So substituting the rest of the values, so Q is 43,000 kilojoule into combustion efficiency 0.96 equals air fuel ratio is given as 15.5 plus 1, this into your Cv, Cv of air is 0.821 into T3 minus your temperature T2, which you have found out to be 732 Kelvin. So with this we'll find out T3 is 3779 Kelvin or 3506 degrees Celsius. So it's close to 3500 degrees Celsius. So now this is a process happening at constant volume. So your P by T is constant. So P3 by T3 will be equals to P2 by T2. So now your only unknown here is P3. So we know T3 we have calculated, we know pressure at state 2 and temperature at state 2. So P3 will become P2 equal into T3 by T2, which equals 2047 kilopascal, which is the value for pressure at state 2 into 3779. So here we have to use it in Kelvin, even though the question asks temperature in degrees Celsius. So here you should be careful when substituting in Kelvin. So 3779 divided by 732. So this gives me 10568 Pascal. And sorry, I think this will be in kilopascal. 102,047 into 3779 732. Yeah, this will be in kilopascal. So it goes to 10 megapascal, 10.56 megapascal. So that is the pressure at state 3. Then T4 is T3 into 1 by RC raised to power gamma minus 1, because again here if you see, go back to the cycle, so volume at state 2 and state 3 is same, and volume at state 4 and 1 is same. So your compression ratio between process 1 to 2 and process 3 to 4 will be same. So it's just the expansion ratio, so it's the inverse of 1 to 2. So again, that is an reversible adiabatic process, reversible adiabatic expansion. So T4 equals T3 into 1 by compression ratio raised to power gamma minus 1. So from this we can find out state 4, so which is 3779 into 1 by 9.5. so compression ratio is given, and raised to power gamma minus 1 is 0.35. so this gives me 1719, or in degrees Celsius is 1446 degrees Celsius. So this is at state 4. So now similarly 3 to 4 is again a reversible adiabatic process. So we can express in terms of pressure and volume, so PV raised to power gamma. So with that, P4 becomes P3 into V3 by V4 raised to power gamma. So this will be equals to P3 is 10,568 kilopascal into 1 by RC is 9.5 raised to power 1.35. This comes out to be 506 kilopascal. So this is the pressure at state 4. So with this we have solved for all 4 state points. So we know pressure and temperature at all 4 state points. So now we can estimate the work done. So work done during the power stroke. So power stroke is the process 3 to 4. Process 3 to 4 is the power stroke or working stroke. So specific work done here is, so is divided by work done divided by mass of air plus fuel. So that will become, so if you see work done for an adiabatic process will be m dot r T2 by T2 minus T1 divided by gamma minus 1. Or sorry, 1 minus gamma, T1 minus T2 is gamma minus 1. So or we can write it in terms of pressure, P1 V1 minus P2 V2 by gamma minus 1. So here we, as we know, in terms we don't know volume, so we can find, we have already calculated the temperature, so we will write in terms of temperature is R T2 minus T1 divided by 1 minus gamma. So your state your expansion is happening at starting at 3 and ending at 4. So we know the temperatures at state 4 and 3. So and R for air is 0.287, so 0.287 kilojoule per kg Kelvin into your temperature 4 is 1719 minus at 3 is 3779 divided by 1 minus 1.35. so this comes out to be 1689 kilojoule per kg. So this is the specific work which is done in the power stroke. Next is we have to find out the heat added during combustion. This is again in terms of specific, uh, so you don't care about the mass. So Q is CV T3 minus T2. So because heat addition is happening between 2 to 3. So CV is 0.821 into T3 is 3779 minus 732. This comes out to be 2502 kilojoule per kg. Next is net specific work done. So to find out net specific work done, so we have already found out work done during the expansion process 3 to 4. Now you need to find out how much work you are giving in for the compression. So practically we saw that is done using the flywheel. So here so we have to see how much work is done during the compression. So again similar adiabatic process, so the same expression R T2 minus T1 divided by 1 minus gamma. So substituting the temperatures, so 0.287 into 732 minus 333 is the inlet value which was given, divided by 1 minus 1.35, which comes out to be minus 327 kilojoule per kg. So it is negative because that work is given to the cycle for compression to happen. So the net work which will happen is W12 plus W34, which comes out to be minus 327 is the compression work which is given in, and 1689 kilojoule per kg which is produced by the engine. So the net work is 1362 kilojoule per kg. So with this again we can find out the thermal efficiency. This net work done divided by the heat added. So this comes out to be 1362 divided by 2502 is 0.545 or 54.5%. So this is one way of solving the efficiency, to find out efficiency. The next is 1 minus T1 by T2, or it become 1 minus 1 by RC raised to power gamma minus 1. So 1 by RC is again compression ratio. So if you see 1 by RC raised to power compression ratio, you can substitute in terms of temperature. So if you see in terms of temperature, T2 by T1 is RC raised to power gamma minus 1. So we can substitute 1 by RC raised to power gamma minus 1 as T1 by T2. So that also can be done. So this comes out to be 0.545 again. So in either way, if you solve, you will get the same efficiency for the Otto cycle as 54.5%. Any doubts in this question? It's all simple. We have solved. We have 4 processes. We used that 4 process to estimate the thermodynamic work and the heat added, and to find out temperature and pressure at each of the state points. And also using this, we found out the efficiency. So if you see, there is no need to remember this formula. If you remember, it's well and good. It's easier to solve. Okay, so with that I'll move to the next question. So similar question, previously we saw for a spark ignition or a self spark ignition engine. Now we'll do it for a compression ignition engine, or previous was a Otto cycle, now it's a diesel cycle. So a CI engine operating on the air standard diesel cycle has cylinder condition at the start of compression of 65 degrees Celsius and 130 kilopascal. So light diesel fuel is used at an equivalence ratio of 5 is greater than or equal to 0.8. So equivalence ratio is nothing but your comparison with the stoichiometric ratio. So we'll see that also. So stoichiometric is when you have complete combustion. So what ratio of air and fuel mixture is there for a complete combustion, and that is your air fuel ratio for a stoichiometric this thing, and that compared with your present one. So air fuel ratio divided by the stoichiometric air fuel ratio will give you the equivalence ratio. So here you are using 0.8, so with a combustion efficiency of 0.98%, so is 0.98, and your compression ratio is as 19. So other observation which you can make is your Otto cycle or your petrol engine will always have a lower compression ratio, and your diesel cycle will have a higher compression ratio. So you can see in the previous problem also it's true practically too. So here your compression ratio was in 9.5, so here it's 19 diesel engine. So it's practically also that's the case, because diesel engine you generally compress it, and because of the compression there's increase in temperature and pressure that causes the combustion to happen. So you generally have a higher compression ratio in a diesel engine. So they have also given stoichiometric air fuel ratio is 14.5. So you know the inlet pressure and temperature, you know combustion efficiency, so calorific value also is same. So it's 500 kilojoule per kg, and your compression ratio is given. So similar to the previous problem, instead of directly giving an air fuel ratio in this question, they have added in terms of equivalence ratio and stoichiometric air fuel ratio. So ultimately, indirectly they have given the air fuel ratio. So similar to the previous one, we have to find out temperature and pressure in each of the state points. C, you have to find out the cutoff ratio. D, indicated thermal efficiency, and E, heat lost in exhaust. So we will see how to solve this. So just like we will convert in terms of Kelvin. So inlet temperature is 65 degrees Celsius or 338 Kelvin, and pressure is given as 130 kilopascal. So at state 2 is again it's a reversible adiabatic process. So T2 by T1 is V1 by V2 raised to power gamma minus 1. So this becomes 338 the inlet temperature into compression ratio 19 raised to power 0.35. This comes out to be 947 Kelvin or 674 degrees Celsius. Similarly, we can find out pressure because it's a reversible adiabatic process. So V raised to power gamma is constant. So P2 equals P1 into V1 by V2. So this comes out to be 130 kilopascal at inlet into V1 by V2 is compression ratio 19 raised to power 1.35. So this comes out to be 6922 kilopascal. So you see here again also comparison I will show. So pressure at after compression is 6922 kilopascal. If you see in the previous case it's 2047 kilopascal. So here diesel cycle is 3 times more. It's all because of the compression ratio. So this is what will cause, and also temperature 674 degrees Celsius, and here it's 459 degrees Celsius. So this basically temperature will be such that it's more than the ignition point temperature required for the fuel. So this will what will ignite the fuel. So next is we need to find out the air fuel ratio. So as I told, equivalence ratio is your air fuel stoichiometric air fuel ratio divided by air fuel ratio. So the stoichiometric air fuel ratio is 14.5 and equivalence ratio is 0.8. So this becomes 18.125. So your air fuel ratio is 18.125, and your with that just like the previous expression, your heat addition is equals to, here it's happening at constant pressure. So this is not CVDT but CPDT. So Q into your combustion efficiency into air fuel ratio plus 1 into CPDT. So change in heat added will be equal to change in enthalpy. So Q is 42500 is the calorific value into the combustion efficiency 0.98, and air fuel ratio is 18.125 plus 1 into your Cp of air is 1.108, or else you can find out 0.815 plus 0.287 you can get, into T3 minus T2. T2 we have found out 947. So with this we can find out T3 as 2913 Kelvin or 2640 degrees Celsius. Again P3 will be equal to P2 because it's happening at constant pressure. So that will be 6922 kilopascal. Then V4 is equals to V1, and from V3 to V4 you can use the ideal gas expression to find out the volume here. So at state 4 is RT1 divided by P1. So here you will get specific volume. So substituting that, we can find out specific volume at state 1 and 4 is 0.7462, and in 3, so this we are doing it to find out the cutoff ratio. So this at 2 to 3, this at constant pressure. So here we have found out specific volume at state 1 and 4, and 3 is RT3 divided by P3. So this comes out to be 0.1208 meter cube per kg. So again T4 is T3 into V3 by V4 raised to power gamma minus 1, because we in the Otto cycle we directly substituted the compression ratio, because both the compression ratio were same, the volume ratios were same, but here the volume ratios are not same. So we have found out the volumes at state 4 and 3, specific volumes at state 4 and 3. So with that, again a reversible adiabatic process. So T4 equals T3 into V3 by V4 raised to power gamma minus 1. So this comes out to be 1267 degrees Celsius, and P4 is again P3 into V3 raised to power V4 raised to power gamma. So substituting the values here will come out to be 592 kilopascal. So we have found out all the pressures and temperature here. So next is to find out the cutoff ratio. So cutoff ratio, if you see, is your volume ratio between the process 2 to 3. So 2 to 3, if you see, it's a constant pressure process. So constant pressure, so from ideal gas you can say your V by T is constant. So your V2 by V3 is nothing but T3 by T2. So beta is actually V2 by V3. So you can either find out just like how we found out V3 and V4, we can find out using an ideal gas equation, find out specific volume at state 2, and you can substitute the volume ratios, or we already have temperature, so we can straight away substitute the temperature. So cutoff ratio will become T3 by T2. So this is because that 2 to 3 process is constant pressure. So you are substituting volume in terms of temperature, which is inversely proportional. So T3 by T2. So substituting that will become beta as 3.08. So next is the thermal efficiency. So this is the indicated thermal efficiency formula. So this becomes on substituting 1 minus 1 by RC raised to power gamma minus 1 into beta raised to power gamma, this beta is your cutoff ratio, beta raised to power gamma minus 1 divided by gamma into beta minus 1. So substituting all the values, we will get 54.7%. So that is the efficiency. So heat lost in exhaust, is you can use straight away CV dt. So you know the temperature at 4 and 1. So 1 is 338 Kelvin and 4 is 1267. So you can substitute CV T4 minus T1 and straight away find out the exhaust Q, and we can also cross check here. So Q is your inlet energy Cp T because at constant pressure. So Cp T3 minus T2, this is 1.108 into your T3 minus T2, which comes out to be 2178 kilojoule per kg. And net work, you can find out just like the previous process, you can find out the net work, and on substituting you will get the similar values, 54.7, and the exhaust is Q minus W net, which comes out to be 987 kilojoule per kg. So any doubts in this question? So okay, then I'll move on to the next question. So this is on a dual cycle. So previously we saw an Otto and diesel cycle. So we'll see a problem on dual cycle. So this is slightly trickier. You see, it's given as a compression ignition engine for a small truck is to operate on an air standard dual cycle with a compression ratio of RC equals 18. Due to structural limitation, maximum allowable pressure in the cycle will be 9000 kilopascal. Your light diesel fuel is used at a fuel air ratio of 0.054. So fuel air ratio is m dot f by m dot a. Your combustion efficiency can be considered 100%. Cylinder conditions at the start of compression are 50 degrees Celsius and 98 kilopascal. So what is we have to calculate? So what is known first? Before going to what is to calculate, we will see what is known. Just clear up. So it is working on a dual cycle. Your compression ratio, that is V1 by V2, volume ratio, is given as 18. Because of some structural limitation, you cannot exceed pressure of 9000 kilopascal. A fuel air ratio is given, and your inlet condition is given as 50 degrees Celsius and 98 kilopascal. So this is all is known. Okay, so next is to find out maximum indicated thermal efficiency possible with this condition. So what can be the maximum thermal efficiency which you can have? Next is peak cycle temperature under conditions of part A. So when you are having a maximum thermal efficiency case, so what is the peak temperature? Next is minimum indicated thermal efficiency possible, and what is the peak case during this peak temperature. So this is operating a dual cycle. So this is similar to the what we saw in the class start of the session today when we compared Otto, diesel and dual cycle. So when we have a constant compression ratio, and so the dual cycle lies between Otto and diesel. So when we have same compression ratio, and there is in this case there's also a limitation on pressure. So this is like combining both comparison. So we'll see how to solve this. So starting, we list out what is known, and at state 1 is 50 degrees Celsius temperature, so it becomes 323 Kelvin, and your inlet pressure is 98 kilopascal. So in either maximum and minimum case, so here we are now, it's a different comparison. What we saw in the previous comparison was we had both compression ratio constant, and it's also limited by the maximum pressure. So maximum pressure limitation comes, in that case you have a diesel cycle which is giving maximum efficiency, and when you have constant compression pressure compression ratio, then your Otto cycle gives you maximum efficiency. So but this is defined by your state 2. Your state 2 is what is limiting in which comparison which you like. So we need to find out pressure at state 2. So if your pressure at state 2 compression is more than your design case, then you have to go with the diesel cycle, because you cannot again add heat and increase the pressure. So we have to see what pressure your state 2 is. So we know inlet condition 1, so we'll find out at state 2. So state 2 is reversible adiabatic process. So we can just like how we solved in the previous case, previous two problems, we will solve similarly. So T2 is T1 by into V2 by V1 by V2. So this comes out to be raised to gamma minus 1. So your temperature is 615 degrees Celsius. So this temperature at state 2. Then your pressure at state 2 is again P2 equals P1 into V1 by V2 raised per gamma. So pressure is P1 is 98, so P2 is 4851 kilopascal. So with this, P3 is maximum pressure which you can go, so it is 9000 kilopascal. So now if you draw in a PV diagram, so you are starting from 1, you are compressing it to state 2. Now this pressure is only 4851 kilopascal. So now you can go either by volume process, constant volume process, where your pressure is increasing and it goes to X or 3A. You can go to 3A, then you are operating as an Otto cycle, and then you can go by a constant pressure process which is 2 to 3. So if you see this the maximum pressure which is there is much above 2. So this comes into the constant compression ratio case. So in this case, the Otto cycle will have the maximum efficiency. So maximum efficiency will be with Otto cycle, but you should go from 2 to 3A. In that case, it becomes an Otto cycle. But if your pressure at 3 is much above your maximum pressure, permissible pressure, which is 9000 kilopascal, then you cannot go. Then you have to opt for a dual cycle with 2 to X being 9000 kilopascal, and then the remaining heat added at constant pressure. So the maximum indicated thermal efficiency, possible when as much of combustion as possible done at constant volume. So it's close to Otto cycle. So now what will happen is 3A pressure will be much larger than your 9000 kilopascal. So we are opting for a dual cycle. So that's what is given in the problem. So 1 to 2, then 2 to X, X to 3B, and then 3B to 4. So this is what our process will be. So your temperature at state X is T2 into P3 by P2. So because this is happening at constant volume, so with this you can find out Tx as 1647 kilopascal. So this we have already found out temperature at state X. So now air fuel ratio is 18.52. So your total heat which you are adding in is mass of fuel into calorific value into combustion efficiency. So which will be equal to your constant volume heat addition and then constant pressure heat addition. So mass of fuel plus mass of air into CV Tx minus T2 plus mass of fuel plus mass of air into Cp T3b minus Tx. So combustion efficiency is 1. So when you divide it by mass of fuel, so this becomes calorific value equals AF plus 1 into Cv into Tx minus T2 plus air fuel ratio plus 1 into Cp T3 minus T2 Tx. So we know all the temperature 2x and we need to find out 3. So if your Q value is equal, your X value is pressure is less than your permeable pressure 9000 kilopascal, or the heat addition is fully at constant volume, then becomes Otto cycle. In this case your T3 will becomes equal to Tx. So when T3 becomes equal to Tx, it becomes an Otto cycle. So this is the other way of checking whether it's an Otto cycle or diesel cycle. So Q, you are substituting the values and you are estimating T3. This comes out to be 3050 Kelvin. So this is much different than your Tx value. So you are operating in a dual cycle case in this case. So your process is 1, 2, x, 3 and 4. So this T3 is again your peak cycle temperature. So this is where your maximum temperature will occur in the cycle. So which was given the question B, sub part of the question. So next is the pressure ratio. So with that we can find out pressure ratio is Px by P2, Px by P2. So this constant volume. So the ratio of pressure there is the pressure ratio alpha Px by P2. So 9000 by 4851 gives me 1.855. Or cutoff ratio beta is T3 by T2. So again this is constant pressure. So you are expressing volume in terms of temperature. So 3050 divided by 1647, this comes out to be 1.852. So thermal efficiency is this is how dual cycle efficiency looks like. So 1 minus 1 by your compression ratio RC raised to power gamma minus 1 into alpha beta raised to power gamma minus 1 divided by gamma alpha into beta minus 1 plus alpha minus 1. So this is how the formula for the dual cycle is. So on substituting we know all ratios and the gamma value. So it comes out to be 60.3%. So with the given conditions, so given inlet temperature and pressure and your maximum permissible limit and the air fuel ratios and so on, with the given set of conditions, this is what the maximum efficiency you can get operating as a dual cycle. So with that condition you cannot go to an diesel cycle, sorry Otto cycle, it's not possible. So you can best possibly operate as a dual cycle, and the maximum efficiency you can get is 60%. So again this is all this is all theoretical values. So the peak temperature which we have already calculated 3050 Kelvin, so minus 273, which will come out to be 2777 degrees Celsius. So that is the peak temperature. Next is minimum thermal efficiency. So again if you remember in the comparison problem, for the same compression ratio, your Otto cycle is maximum, gives you maximum efficiency, then comes dual, then comes diesel. So diesel will have the minimum efficiency out of 3. So to operate as minimum thermal efficiency, it has to operate as a diesel cycle, and combustion will happen at constant pressure. So with this your state at 1 and 2 will remain same. So T3 will, you can estimate T3 as heat being added as constant pressure. So AF plus 1 into Cp T3 minus T2. Your temperature T2 is same as 888 and other values all same. So substituting that you can estimate T3 as 2853 Kelvin. So if you see here, your temperature is much smaller than what you got in dual cycle. So cutoff ratio here is T3 by T2 again. So it's constant pressure. So this comes out to be 3.213. So substituting in the diesel cycle efficiency formula, so 1 minus 1 by RC raised to power gamma minus 1 into beta raised to power gamma minus 1 divided by gamma into beta minus 1. This comes out to be 53.3%, and your peak temperature is 2580. So what we know here is we have made a comparison, and we have found out that when operating as a dual cycle with a set of conditions, you are getting a maximum possible efficiency of 60%, and the minimum which you can have efficiency is like operating in a diesel cycle, and the efficiency will drop down to 53.3%. So that's what we'll conclude. Any doubt in this question? Okay, if not, we'll move to the next question. So this is somewhat related to the combustion, thermochemistry and combustion related question. So we have a fuel, the formula C4H8, which is burned in an engine with a fuel rich air fuel ratio. Your dry analysis of the exhaust gives the following volume percents. So CO2 is present as 14.95%, and the fuel is present in 0.75%. The carbon monoxide is 0%, your hydrogen is 0%, oxygen is 0%. So with the rest being nitrogen, higher heating value of the fuel is 46.9 megajoule per kg. So write the balanced chemical equation for 1 mole of this fuel at this condition. Then calculate air fuel ratio, equivalence ratio, lower heating value of fuel. D. Energy released when 1 kg of this fuel is burned in the engine with a combustion efficiency of 98%. So this is what you have to find. So what is given is a molecular formula for the fuel is given, and it is operating as a fuel rich air fuel ratio. So that means your fuel content is more compared to the stoichiometric fuel air fuel ratio, and a higher heating value is given, and the percentage by volume, so by volume is similar to moles, so you can cross with moles also, but you cannot use in terms of mass. So then you have to find out the molecular weights. But here, so that volume percentage is given. So we'll see how to solve this. So first, an unknown amount of fuel. So we don't know how much amount of fuel is burned. So we'll assume some amount, X amount of fuel is burned with Y amount of air. So this is how the expression will be. So X into X moles of your C4H8, which is the fuel, is burned with air. So air contains 1 mole, and because 21% oxygen and rest being nitrogen, assuming nitrogen oxygen mixture, you assume that air is made of only nitrogen oxygen and you neglect the other components. So this is how it will be. So 1 mole contains 3.76 moles of nitrogen. So Y moles of oxygen plus Y into 3.76 moles of nitrogen gives you 14.95 moles of CO2 plus 0.75 of the fuel plus 84.3% of nitrogen, plus you have combustion will result in water, So that contains Z amount of water which we have to find. So now this is how the expression looks like. So doing an nitrogen balance, so we can find out straight away the Y amount, how much of air is being used. So Y is 3.76 into 3.76 is equals to 84.3. So this gives you Y 22.42. And then similarly for oxygen, when you balance oxygen, we can find out the Z value, amount of water which is formed. So 2 into 22.42, which is Y, because here is O2, here is 1 O, so 2 times of Y is on the left side and Z times on the right side, and plus 14.95 into 2. So 2 into Y 22.42 equals 2 into 14.95 plus Z. So with this we can find out Z as 14.94. And then when you balance hydrogen, so you can do the other also. If you want, you can do carbon balance. So you can, here we are doing a hydrogen balance. So hydrogen balance becomes 8 times X on the left equals 8 into 0.75 plus 2 into 14.94. So this comes out to be X is 4.485. So when we put this in the reaction equation, so this is how this will look like. This is the actual expression. So dividing by 4.485 to make it 1 mole of your fuel. So this becomes 1 mole of your fuel, becomes 5 of moles of your air, and the rest is right hand gives you the expression for the products which is formed. So the air fuel ratio is nothing but mass of air divided by mass of fuel. So mass you can convert into moles as your moles is mass by molecular weight. So your mass will be moles into molecular weight. So mass of air is moles, number of moles of air into molecular weight of air divided by moles of fuel into molecular weight of fuel. So if you see here, your air is 5 into air contains 4.76 moles of gas. So 1 mole of oxygen plus 3.76 moles of nitrogen. So you are using 5 times the moles of air. So 5 into 4.76 into your molecular weight is 229 for air divided by 1 mole of fuel into, if you see, calculate molecular weight for C4H8. So 4 into 12 plus 8, it comes out to 56. So molecular weight of fuel is 56. Substituting this, you can find out air fuel ratio as 12.325. Next is to find out the stoichiometric reaction. So stoichiometric reaction is the complete combustion. So here if you see, we had 0.75 percentage of your fuel which is present at your product. So that didn't combust. So that was leftover fuel. So if you that's for complete combustion. So this is how it will look like. So you assume 1 mole of fuel plus some mole Y moles of air, and it forming CO2, H2O and nitrogen. And similarly you are doing carbon, hydrogen and oxygen, nitrogen balance, you can find out each of the coefficient, and this is how the expression will look like for a stoichiometric reaction. So with this we can again find out the air fuel ratio for stoichiometric value, and it will come out to be 14.79. So this is the stoichiometric air fuel ratio, and your equivalence ratio will be stoichiometric air fuel ratio divided by air fuel ratio. So 14.79 divided by 12.325, so it will come out to be 1.2. So next is to find out your lower heating value. So lower heating value is nothing but your higher heating value minus your latent heat of water which is there. So your if you are condensing the water, so that amount of heat is also added, and that gives you higher heating value. So QLHV, the lower heating value is higher heating value minus your latent heat of water. So for 1 kg mole of fuel in stoichiometric reaction, there is 4 kg mole of water. So for higher heating value and lower heating value, we will use the stoichiometric reaction. So for 1 mole of fuel, your latent heat for vaporization is 4 into 18 into 2442.3. So this because 1 mole gives you 4 moles of water, and your weight is 18 to convert into mass, and 2442.3 is kilojoule per kg. So substituting that, it will give you 175.85 megajoule. So HFGA is taken at 25 degrees Celsius. So assuming that is the room temperature, ambient condition. So for 1 kg of fuel, your enthalpy of vaporization will be 175.85 divided by 56. So previously it took it for 1 mole. So to convert into 1 kg, we are dividing it by 56. So it gives you 3.1 megajoule per kg of fuel. So your QLHV is 46.9 minus 3.1 will give you 43.8 megajoule per kg. So you know the QLHV. So using this is the calorific value. So Q is mass of fuel into calorific value into combustion. You're using QLHV value here. So mass of fuel is 1, and QLHV, because this is written in terms of kg. So per kg how much heat is generated. So 43.8 into the combustion efficiency is 0.98. So that gives you 42.9 megajoules. So any question in the previous one? So this is the final question problem which I have. Okay. So with that, we move on to the last problem. So a flexible fuel vehicle operates with a stoichiometric fuel mixture of 1/3 isooctane, 1/3 ethanol, and 1/3 methanol by mass. So for this we need to find out R fuel ratio, your MON, RON, and sorry, I forgot this abbreviation. It's for octane number. A is Antonov index, and MON and RON is for octane numbers. Just a second, I'll find out MON and RON. MON is called as motor octane number, and RON is the research octane number. So we'll see how to solve this. So there's a table given for the fuels. So we are using isooctane, ethanol, and methanol. So for one in terms of by mass, so 1/3 by mass. So we are writing in terms of mass. So for isooctane, then methanol and ethanol, so all 1/3. So we are taking So if you're taking 3 kgs, so each will have 1 kg. So 111, and molecular weight of each of the fuel is isooctane is 114, then methanol is 32, ethanol is 46. So with this we can find out the moles for per kg. So 1 divided by 114 gives you 0.00877, and so for methanol is 0.03125, and ethanol is 0.02174. So if you see, the number of moles is 0.06176. So we can find out the mole fraction here. So mole fraction will be your number of moles of octane, isooctane, divided by total number of moles. So 0.00877 divided by 0.06176. This gives you 0.142, and again for methanol is 0.506, and ethanol is 0.352. So you can find out stoichiometric reaction. So if you assume 1 mole of your mixture is considered, so that contains 0.142 moles of isooctane, 0.506 moles of methanol, and 0.352 moles of ethanol. This is combusted with air, some Y moles, and this gives you CO2, H2 and N2. So when you do an carbon balance, hydrogen, oxygen, nitrogen balance, so this is what you get for a stoichiometric reaction. So with this we can find out the air fuel ratio. So air fuel ratio is mass of air divided by mass of fuel. So again we have found out in terms of moles, so we to substitute the molecular weight. So your mass of air you are using is 3.59 moles into 4.76 into molecular weight or molar mass is 29, divided by your molar mass for fuel, because the number of moles is 1. So 0.142 moles into 114, which is the molecular weight or molar mass, plus 0.506 into 32 plus 0.352 into 46. So this gives you 10.2. So that is the air fuel ratio. So octane number, so this is just an octane number. So motor octane number and research octane number is given by so RO and research octane number. So it's all data which is given. So they are just named it to to compare. So but it's one and the same. So octane number we will calculate. So how to calculate is octane, isooctane is how it's defined. Octane number is give you 100. So isooctane is 100, and you compare it with the other fuels, and your isooctane. So if you see, octane number is 100, and methanol and ethanol is what is used. So methanol is 92 for MON and 89. So each are in 1/3 ratio. So you multiply it with the respective octane numbers. So it will give you 93.7. So here you have to find use the mass ratio or mass fraction to find out the octane number. So mass fraction into individual octane number will give you the effective octane number of the fuel. So that is 93.7, and your research octane number is 104.3. Your fuel sensitivity is the difference between these two, which is 10.6, and your anti-knock index is your average of this, so that is 99. It's just to compare with your isooctane. So now we are having blends of fuel. So India is trying to mix ethanol and to increase your so the coming engines are more capable of having ethanol mixture, so it can run with ethanol mixture. So this is just an idea to show how, if you want to compare, so how will it be. So we have derived an expression. So and then so if you want to find it, the octane number, so octane number is used to find out if there will be knocking or not. So if you have more octane, so there is less chance of knocking. So knocking is there is a combustion happening before self ignition, which is happening, and that creates a increase in pressure, and that will cause vibration and damages and so on. So uh, that is useful to find out whether that will happen or not. So we use an octane number. So this is how we calculate it for a mixture. So with this I have finished what I prepared for today. If you have any doubts, you can ask either in this or what we saw in this week or the previous weeks. So if you don't have any doubts, we can end the session. If you have any doubts, I'm happy to answer. Okay, then thank you for joining. If you have no doubts, we can close the session. Thank you, and we'll see next session.
Thank you, sir.
Thank you. Masurity. Hello.